I'd like to welcome everybody to the March 2026 DAS meeting. Here's everybody present. Say hi, everybody.
Hi, everybody.
Anybody new that'd like to introduce themselves?
Okay.
Anybody new to the club?
Even if you wouldn't like.
Even if I wouldn't like to. All right. So first thing, real quick, we're going to have Easton say a couple words about the Messier Marathon because he's got some setup to do.
Hi, everyone. My name is Easton Honecker. I'm an astronomer from the University of Delaware. So this weekend here, we are hosting our second annual Messier Marathon. It's a public event for the observatory where basically we try and take guests through as many of the Messier objects as we can using the 4-inch, the 24-inch, and the 10 to the 11 inches upstairs. With that said, I'm still looking for some volunteers to help with that event because I found out today we're at almost 30 people. So it's going to be huge. To that end, Rob has been very kind and agreed that we can use some of the DAS telescopes down out on the grass. So we could use a few extra hands, people who are confident and would like to help show the public a lot of these Messier objects. So if that's something that interests you, it's happening this Saturday here from 7 p.m. until midnight. We'll have some food, we'll have lots of guests and a lot of chance to share your expertise. If that's something that interests you and you want to help, please reach out to me. I'm going to write my email on the board and I imagine you can throw it in the chat.
Yeah.
Would you want us to remember, you see the number of folks here. We also, we have a total membership of about 145. Would you want us to send another note out to the broader group?
Please do.
Okay, happy to do so.
Anybody who's comfortable using your equipment down on the solenoids and all that, please reach out. Be happy to have you.
And I mean, probably could even use some, if there are people that are, let's say, not too comfortable with equipment, you could probably still use extra hands to do something, right?
Yep.
So no experience needed?
Yep, just reach out to me and I'll find some way to make your help count.
Cool.
Wonderful.
Thank you, guys.
Thank you.
Thank you very much.
We'll be right here.
Is it rain or shine?
Well, so I said second annual, right? Because last year we had a surprisingly great success despite the clouds being all over. Because one of the things we use is a remote telescope in Chile, the Cerro Católico. So we were able to get a bunch of strong argument.
Nice.
Let me finish this thing. We were able to get a bunch of images last year. I'm hoping to build off of that and have more success this year, but we'll find out. If it's
So,
raining, I will make a call closer to the event.
okay. So
We'll see.
potentially rain or shine.
Potentially, we'll find out.
Yeah.
Okay.
Great.
Wonderful.
Thank you guys.
Very much.
Great work
See you there.
spearheading that.
Appreciate it.
Wonderful. So next thing, did you want to announce the outreach events real quick?
Oh, sure.
Cool.
Hi, I'm Jim Kirshen, the outreach education chair of the DAS. We have an outreach event that's coming up at the Newark Reservoir in conjunction with Cocoa and Constellations, put on by the Newark Parks and Recreation Department. And it goes from 7 to 9 this Friday. I'm hoping that we have at least a small window. Yeah, I know. Hoping that we have at least a small window to observe. It won't be the first time that we've been clouded out at that event. 2 other times. So keep our fingers crossed.
That is not rain or shine.
Oh, no.
And when are you gonna make a final call?
Probably about noon on Friday.
Day of.
Yeah,
Okay.
noon.
And that usually gets, if it's good weather, actually, even if it's not good weather, that usually gets a huge turnout.
Well, they've got 150 signed up.
So all the help you could get would be welcome, I'm assuming.
Absolutely.
And again, for anyone present, it's not too late. If you don't have a telescope, we have a loaner that you can take home tonight to use for that event.
Well, that's true. The nice thing is, the people come out and they like to chat. And even if you don't have a telescope and know something about the solar system or the stars or anything, I'd like to chat that up too.
Mhm.
So it's a fun event.
And yeah, and I say, don't think you're not smart enough, because anyone in this club is way smarter than the average member of the public. So.
It-
In terms of astronomy.
Yeah.
It definitely is a lot.
There we go.
That's great.
Thank you very much.
More knowledgeable.
Thank you very much.
More knowledgeable.
Next, Bill, do you want to say anything about the APC?
Yeah, the next meeting of the Astrophotography Special Interest Group will be on Saturday, March 28th. It's a week from this coming Saturday. The details will be announced on das@groups.io by email. So if you're not signed up for that, be sure and sign up for it. Okay.
Okay, very nice. Sydney, did you want to say something about the election?
Yes, thank you very much. Can you guys hear me?
Yeah.
Oh, yeah, we hear you.
Okay, good. Apologies, my camera's not working. Good evening, everyone. My name's Sid, and I'm the elections chair for the Delaware Astronomical Society. And every couple of years, we hold elections for the board members. And that would be the office of the president, vice president, treasurer, and secretary. And if you are a DAS member of good standing and you think that you could run for any of these offices, just feel free to email me, sidastronomy@yahoo.com. And it doesn't have to be yourself. You may nominate somebody, but my request is to simply just send me a short write-up of who you are, and we'll publish it on the next issue of the Focus. So if you think you're willing or you have the talents to be one of our board members, you're very much welcome to nominate yourself or nominate somebody else. Yeah, that's about it. And thanks so much, Rob. Appreciate it.
Very much, Sydney. You're doing a great job. So next item, Mary, do you want to talk about the book club?
Yes, good evening, everyone. The book club will meet on next Thursday, March 26th at 7 p.m. via Zoom. I'll be sending the invitations out in advance of the meeting with the Zoom link. We will be honored to have with us Professor Alexander Boxer, PhD. He wrote A Scheme of Heaven, The History of Astrology, and the Search for Our Destiny in Data. And Alexander Boxer is really one of the most well-educated, impressive authors we've had join us for the book club. He has a PhD in physics from MIT, a master's in the science in the history of science from Oxford, bachelor's degrees in physics and classics from Yale. And that broad, incredibly impressive education is really brought to bear fully in his work, A Scheme of Heaven. We're honored to have with us again our author from January, Professor Robin Arianrod, who is the author of the book Vectors, and she will be leading the meeting because I thought it would be good to have one mathematician in dialogue with another mathematician data scientist. To give you just a very short taste of what's in the book and the quality of the writing. For starters, this is a quote, for starters, the questions astrology asks, questions about the patterns of the universe and our place within them, are about as deep and as captivating as they come. If there really is a way to tap into the hidden rhythms of the cosmos, wouldn't you want to know about it? But even more intriguing, at least from where I stand, is how astrology uses mathematics and data to investigate these questions. Over 2,000 years ago, astrologers became the first to stumble upon the powerful storytelling possibilities inherent in numerical data, possibilities that become all the more persuasive when presented graphically in a chart or figure. Although it took a while for the rest of the world to catch on, the art of weaving a story out of the numbers and figures, often to encourage a specific course of action, is used everywhere today, from financial forecasts to dieting advice to weather models. The discovery of the interplay between supernovas, the solar cycle, and cosmic rays has taught us that Earth is not a planetary bubble, untouched by the faraway stars. Today, we recognize that we are, and we always have been, creatures of the cosmos. The awareness that our lives are influenced by events in the wider universe has been the basic intuition of astrology from the beginning. Modern science, it must be admitted, has vindicated this intuition, even if, as so often happens, not at all in the way it was originally imagined. I hope you'll be able to join us. Please feel free to share the invitation with anyone you believe would be interested in joining us. They'd be most welcome. Thank you.
Thank you, Mary.
Thank you very much, Mary. That was wonderful. Very nice story. Now, the next item here is in the hallway. When you guys were coming in, I know you folks online couldn't see it, but in the hallway, there is a telescope set up directly to the right. That telescope was just recently donated, and we're hoping to get it in the hands of someone who can use it for good purposes, for astronomy, to look at things and enjoy the night sky. So please feel free to check it out. It's right there in the hallway. We'll be cleaning it up, making sure everything's ready, and then we'll put it in a silent auction in the fairly near future so that we can put it in the hands of someone who could use it for good astronomy. Very exciting. And one final thing is that we recently reached out to see if anyone had experience with different t-shirt marketplace websites like storefronts and other things like that. You probably noticed the email that went out, and you probably saw it in the focus. We did get a bunch of feedback about different services that are available, and we got some feedback from people who have experience with that with their work and stuff like that. What we haven't got yet is somebody who's willing to spearhead the effort, investigate all the different things we've collected, and find out which one we'd actually like to use and set it up for us. So we're looking for a great DIS volunteer out of our 145 members who would be willing to help us out. So if you'd be willing to check that out, please contact us. You can email my message that was sent out, dispresident@delastro.org, and just reply to the meeting invite that I sent, and we can definitely set you up. We have done a whole bunch of research. We have a whole bunch of sites that are possible. And once you set it up, I'll be glad to stick it right on the website. I'll set up a web page for it and everything. But we need somebody to do that legwork, check them all out, and see which might be a good site to do, which would be a good one to use. In a related note, we got our 70th anniversary coming up, and I'll be sending out some invitations to send in photos and stories and stuff like that so that we can have a nice meeting in November having to do with our 70th anniversary. We'll tell stories, we'll share pictures, we'll share all sorts of things. So I'd like to start gathering that stuff earlier than that. So I'll probably be sending out an email asking you to send in your stuff. That's all the announcements on my list. Does anyone have any more announcements? All right, let's get started then. Without further ado.
All right. Thanks, Rob.
All yours.
So for our main talk today, we welcome back our NASA Ambassador John Conrad. He's given us a bunch of great talks in the past, keeping us up to date with what's happening with NASA. And today he joins us to share some interesting information about cosmic collisions, from the local scale, collisions within our solar system, all the way up to the biggest scale of the imminent crash into Andromeda. Yeah, John, welcome back. The floor is yours.
I hate to correct you, it's not it.
Relatively speaking.
I'm gonna go home.
Relatively speaking.
It will be a big deal.
Are you guys seeing the slide deck online now of Cosmic Rex, John Conrad?
Yep, you have to share it.
I thought we already did that.
No,
Really?
no. Share button.
Okay.
You can get rid of that.
We've only been doing Zoom for 7 years, John.
You can get rid of that.
Yeah, I don't know how. Where's...
Well,
Oh, there it is. It's like 18 windows all mushed on top of each other.
And pin that.
Pin, confirm. And then we're gonna do this.
And there's a place to choose sound off too.
Sound off? Oh,
Yeah.
to mute everybody?
No,
Oh,
no, it's from the slides.
oh.
Because there's one that's noisy and I don't want to bother.
Got it. Do you know where that is, John?
I don't know where the button is.
How about this?
Unless I drive. So.
Yeah, so you're
No,
welcome.
I can't.
All yours.
I can't. I'm not sure exactly where you are.
You know what? If it's noisy, life will go on.
Sure.
Are you all set?
I am. Do we have a clicker or should we use mine?
Um,
The drawer.
I've got one here. Let's see if we can get it set up real quick.
Well, here, if it's just a matter of plugging into
You got one? Cool.
the standard
Yep.
USB.
And let's see if it works. I'll get you to presentation mode. Give it a shot.
Looks good.
You're all set. John, the floor is yours.
All right. No, do that. And dimmer. Hello, everybody.
Hey, John.
I love giving these talks and I love seeing you guys, a lot of old friends here. So, and I don't think I've been here in a year or more. So at any rate, lots of things have come out of NASA, and what's been interesting in the last year, among other things, and you can kind of guess why, is the NASA speakers have been kind of quiet. Being a government agency, you can guess why. But at any rate, the university people that are doing astronomy get in there and they give us lots of good talks. So a lot of the material you're going to hear is not actually from NASA researchers so much as it is from a number of different universities. And I'm taking advantage of that. It did come to the ambassadors through NASA. And so we're going to be talking about cosmic wrecks tonight. There are some really interesting ones. I always like to start off with
We got your tighter. Rob, do you know how to fix that? Yeah, so there's a lot of clutter on your titles. I'd like to
That
clean
can
up
be
for you.
X that.
Okay.
And then second thing, let's just see if we can do that. Where's the hide button? Hide.
There we go.
Can you still drag it out of the way? Yeah, I was just thinking that. Hide floating meeting controls. There we go.
Now we're cooking.
And so I like to start with the context always, and
Thanks, Rob.
I chose to pick a fairly large context, like everything. Space, unimaginably large. And I've pondered this lately because I've given this talk a number of times. We, of course, all know that the universe began 13.8 billion years ago. And we know that it started from this singularity, which was all matter and all energy, and it began from there, and it's been expanding ever since. So I say that a lot, and then I think, what was that singularity in? And I mean, was it in space? Because no, there wasn't any space. Right. At any rate, we sort of take for granted things that have been coming on board in our understanding for about the last 50 years now, or in the case, this name we give it, the Big Bang, from Hoyle back in the 50s, I think. And it's as if we actually know this stuff. And I just challenge you all to step back and think about that, and think about what it's expanding into, and the fact that we actually don't understand an awful lot at any rate. So, but we do believe, and the physics and cosmology that we've been able to do says that it isn't just the matter that's in space that's expanding. I can get this to work. Let me click the side.
Oh, yeah.
Clicking on
Click in the slide. You should be all set, John.
Mouse click into the slide area, into
The mouse.
yeah.
Just click on the side.
Yeah.
Just click on it somewhere there with the mouse.
And I have to click,
then-
okay.
and then-
Just once. Now you should be good.
And now it should work. Okay. And if it dies, I do that. I haven't used a mouse since about 93. I think. Anyway, so the other side of everything, of course, is the matter that's expanding into space. And you think about that, and you realize that it's not actually matter that's expanding outward, it's space that's moving outward, whatever that means. At any rate, fortunately, the matter isn't really all expanding away from everything else, because if it were, then all we would have
would be the most primitive things and nothing clumped together, but we have this wonderful thing called the force of gravity. And so thanks to the force of gravity, things clump together like stars and moons and planets and elements and us. And at the beginning, of course, we had just a couple elements. Literally, in the first very short time, we had the same ratio of hydrogen and helium that exists today, about 3 to 1. And we come out of those elements, and the rest of the elements all got cooked up in stars or catastrophic things that happen when stars die. And so secondly, let's just think about this, the more general things as they move around, because everything moves. Angular momentum is conserved everywhere. And so everything starts to move and continues to move. And things sometimes like large clouds of molecules will finally start to pull together under gravity, and they'll form things, and they'll be disks, and they'll converge on themselves. But once they are solid objects, then they will be converging with each other based on the attractive force. And sometimes they'll merge, sometimes they'll actually collide, sometimes they'll come close, and if they slightly miss, they'll go into orbit around each other. Something may come by that's more attractive, and they'll diverge off and follow that object. But there's movement all the time, with everything spinning all the time. And so that means that there are going to be lots and lots of collisions through time, which we'll call the cosmic wrecks. And we're going to start off far away, and then we're going to move inward in a couple steps until we get inside the solar system and talk about the collision of different types of objects. And so we're all familiar with these wonderful space telescope images. This happens to be the latest and greatest, which is from James Webb. And I think they had it out within 6 to 12 months of the operational state, which came about in the middle of 22. So we're now, 3.5 years, going on 4 years into operations of James Webb, and it's been fantastic. But we get these images, and in this case, this is looking in an extremely dark place in the sky with no bright foreground objects at something about the size of your thumbnail at arm's length. And within that, you see that number of galaxies. Everything pretty much there, except what you see with the diffraction spokes there, is a galaxy. And some of them, as you can understand, are extremely dim. And those are actually the most exciting ones, of course, because those are the ones that are going to be the furthest look back time, the deepest objects, the oldest objects. And so if in this tiny area, just that size, there's 100,000, it doesn't really surprise us then that there are trillions in the universe. Numbers are kind of meaningless, but they get up there in a way that we can kind of understand. Everything is receding from everything else because the universe is actually expanding, or is everything receding because there is actually some structure. And the highest element of the structure is the galaxy clusters. You've probably all seen the pictures of the cosmic web that we've been able to plot based on measurements and based on simulations. And so this cosmic web has as these nodes, these galaxy clusters of hundreds to thousands of galaxies that are in fact gravitationally bound and acting on each other. And at the next lower scale, the one that's nearest to what we owe, and I wanted to mention that superclusters, clusters of galaxies, actually are receding. The clusters are receding from each other, and the superclusters don't exhibit the same kind of gravitational collections. And so finally, down at a lower scale, we have the local groups. What does it say? There are tens or dozens of galaxies that are in fact bound to each other gravitationally and interacting with each other, as somebody happened to mention. The two largest ones in our local group include the one that we're headed for, Andromeda, and we'll talk about both of those. And interestingly, and this was some research just last summer, they've now been able to plot out sort of the dark matter block that we seem to find that is influencing the movement of these two large galaxies relative to one another and millions of light years apart. And so this is one of the latest findings. And of course, you don't see the dark matter. You just are able to infer it from the math and the gravitational movements. So let's look at our local group, and we'll start with home. And so there we have a wonderful selfie, except a selfie really is something where the camera is looking back at the object that you want to see. And we don't yet have a camera outside of our galaxy. We don't even have a camera that's very far outside of the planetary part of our own solar system. We don't even have a camera yet, and we're far from it of having a camera outside of our solar system. So it'll be a long time before we get something like that. But in fact, what you can do, as we probably all have done with our cameras, is stand in one place and do your 360 panorama. And so the Gaia, European Space Telescope, did this for several years from our place about halfway out one of the spiral arms of our own galaxy, and gave us this wonderful view with the bright center and the bulge and the halo and a lot of dark clouds that are just way too much matter to be able to see through. And so I blocked out there something you're probably guessing and are familiar with, the other two nearby galaxies, which are known as the Magellanic Clouds, because they're viewable only from the southern hemisphere, and therefore until explorers like Magellan spent months and years in the southern hemisphere in the night sky, the crews and the other people didn't get a chance to observe these wonderful clouds of stars. And when they did, they happened to give their name to it. There's a large one and a small one. And it says satellite galaxies of the Milky Way, that they are bound to the Milky Way, orbiting it. And yet there's been research that said maybe that's not so, but the most recent research, and I did look it up just this week, does again indicate that we think they're gravitationally bound satellites. So here's our nearest neighbor, and it's so near, it's only 15 million trillion miles away. So think about that distance, if you can imagine it, and the fact that there are trillions of galaxies, and you start to understand just how big space is. At any rate, we're fortunate to have Andromeda with a particular orientation where we can look back and forth at each other and see us tilted. So we get a chance to see its spiral arms and its center and so on. And you can tell from the sawtooth edges that this is a mosaic of many, many small staring views taken by Hubble, over 600, and took a decade to put this whole thing together. But that's the most detailed and beautiful view we have at this point of Andromeda. And then once they got that, I thought you guys as astronomers would be interested in this. It doesn't have anything to do with collisions, but because they had the data and they had the spectral data, they were able to slice it time-wise by look back time, by the redshifts that they were observing, and be able to break it apart into the different, if you will, epochs of the formation of the galaxy. And so here are the two most recent slices that they calculated out that go out to about 500 million years ago. And that's fairly recent, actually, on the scale of Andromeda and most galaxies. And you can see that that's where most of the structure, the arms, the clusters, the star birth that's going on, as opposed to the much older parts, the much older material in Andromeda, which is much smoother at this point and doesn't show so many features, actually. So now we'll come back to home. Here's the Milky Way again. And what I'm now showing is that the galaxies, the large galaxies like us and Andromeda, are more ecosystems in that they have a number of gravitationally bound other galaxies and objects that are orbiting them. And in this case, I'm showing you not all of them by any means, but in the little boxes, are 1, 2, 3, 4, 5, 6, 7, 8, and then large and small Magellanic Clouds. So 10 different orbiting galaxies. And the large box in each case blows it up so you can kind of see the shape of that galaxy. And this is very typical of an ecosystem of a galaxy. They're gravitationally bound and they orbit the center of the galaxy. And over time, just as the Earth satellites will decay over time, and in this case, when we talk about time, we're talking about 10, 100 million years, they will move in towards the center and eventually merge with the disk of the Milky Way in a way that it won't actually be on a macro scale visible. In other words, it's a very smooth and minor merger as opposed to some mergers of galaxies. So now let's look at our neighbor again here, and it's a fairly familiar view that you see there of Andromeda with two other Messier objects, Andromeda being M31. And here are the two objects that are tucked in close there that we're going to talk about a little bit now. But I just want to get you sort of oriented to the center of that ecosystem, because here it is now as I have moved out to a larger scale by far. And there you can see the previous image for scale, and you can see what we now have been able to observe. This is not noise, it's not artifacts, it's actual observations that our telescopes of various types have been able to take of the region around Andromeda. And so some of the features are really quite interesting. You see these streaks, which you can imagine long ago were something that merged with the disk of Andromeda, and as it was pulled in, it left gravitational tidal tails, they're called, of stellar material that were just sort of dragged out behind during the merging process. And there are three different colored ones there on the left. There's the giant stellar stream below the disk, and there's some up on the upper right, the northwest side as well. And then I'm going to highlight some other galaxies, like the Milky Way has orbiting galaxies. These are all known as dwarf spheroidals, which is fun to say 3 times fast. So give it a try sometime. At any rate, just for clarity, I want you to know what this is. You probably already guessed. It's a familiar object to us, Triangulum's galaxy. It is not bound to the M31 ecosystem, but it is visible in the field of view here. So we're going to talk now some about these spheroidals. There are 32 of them in the system and the streams, and they indicate a very turbulent past over the billions of years that Andromeda has been, if you will, evolving through collisions or mergers, call them what you will. So now let's look at a different way of viewing those spheroidals. It's the same system here with M33 in the lower left there with its gravitational system, and M31 in the very large circle. And each of the red items that you see there has got a label, and they have a special numbering system for dwarf galaxies. And like I said, there are 31 of them, and they range over a large size range, up to this very large one, 20 million suns, if you will, in mass, down to one that's 3 orders of magnitude smaller. And the 20 million sounds pretty big until you compare it to the fact. And now you know it's a dwarf because Milky Way and Andromeda are about 1 million solar masses, I'm sorry, 1 trillion solar masses each. And until fairly recent years, at least in my reading, we thought Andromeda was quite a bit bigger. And it turns out that now the estimates of the two have sort of come towards each other, towards we now believe that they're both on the order of 1 trillion solar masses. A typical large galaxy. Here's yet another view of the Andromeda system and the dwarf galaxies with a very interesting feature. There are a couple of these features about the dwarves that are the subject of a lot of study because they sort of stand out and we don't understand why. And you see the red ones there, they're labeled in red because they happen to lie on a plane pretty much, orbiting as a plane around the center of M31, as opposed to the other half of the dwarf galaxies. And how they got clumped together in a single plane is at this point mystery and doesn't fit any of the simulations that they've tried. Another feature of the distribution, if you come around to the side of Andromeda and look at Andromeda with Milky Way off to the left, it turns out that the dwarfs are all mostly on one side of the center, what you would think would be the center of orbiting of everything around the center of M31, and yet it isn't. And so we're very much trying to understand why they are all sort of displaced out of where you might expect them to be distributed. And so there are a couple theories that have been developed. And here again, we'll look at the large ecosystem, and we'll look at these two objects, two other Messier objects. The one that's tucked in close there we saw before, and I'm sure we've all I imagine we've all had the opportunity to look at Andromeda through the eyepiece and then be able to pick out M32 and what, 110. And in this case, there's the Triangulum galaxy down here outside of the Andromeda ecosystem. And so we think these two might be the basis for some of the significant things that you're seeing based on what happened in the past to form them. And so we'll look first at the theory of what's believed about M32, which at some time, maybe a couple billion years ago, was a much larger spiral galaxy, in fact, as a progenitor to what it is today. And it and Andromeda, which was much smaller then, came towards each other for over this long period of time, and then gravitationally started to exchange material until they came together into the final state, where M31 was much larger now, having stolen most of the material from M32, which is now a compact elliptical, close into the disk of M31. So that's one of the theories. And this orange stellar stream that you saw is believed to have occurred in that same merger of these two progenitors. And it's thought, and I can't explain how, but that perhaps in that merger, the center object, M31 itself, was displaced within its own ecosystem. The other theory has to do with the Triangulum galaxy, which you see over here on the left. That's M33. And there's a little box in the middle, which indicates the time of M33 approaching Andromeda and then passing close to it about 2.5 billion years ago, at which point it exerted the most influence before it then moved much further away until it's where it is today. But because of that influence, it took the disk of M31 and it caused it to be quite, if you will, warped. Now, this is a graphic that's exaggerated because, as we can all see from the wonderful images of M31, you don't see that at a glance. But apparently, measurements show that kind of warping on the external areas of the spirals. And so again, that's a change from the distant past caused by the passing of this large Triangulum galaxy. And that one, it is kind of easy to understand how it might have displaced M31 from its near neighborhood, if you will. So now I just thought I'd give you a sample here. You may have seen this from the Hubble catalog. There are, I think, 45 examples here of galaxies that are merging, colliding, or have just finished merging. And they're just kind of fun to look at. But the points I want to make is that this is a very small subset of what Hubble has already seen, because in fact, 5 to 10% of galaxies are either in a merger state or recently were. from what we're now able to tell from that catalog. So it's not an uncommon thing at all for there to be galactic mergers. That may not surprise you, but it is a fact. And it is this collision that we talk about, which is the initial gravitational approach and then literally passing through one another, is the first stage in eventually merging together. And we'll show a simulation of that in a minute. And a few, there's so many of them, that some are kind of fun to look at and instructive, like the antennae, which you've probably seen, but those tidal tails just kind of give you a feeling for the past and where things came from and how they finally sort of embraced. And in the embrace here, you can see as you look up close that there's a lot of blue region, which is typical of at least one of the galaxies during the process of merging, because as they pass together, and you've probably heard that since stars are so far apart, they don't hit each other. But in fact, where there are densities of stars and material that pass through and are multiplied in that passage, you get clumps of matter that lead to what they call starburst regions. Lots and lots of starburst. And you can see the blue there for that. So here are a couple others that are fun, like the mice with its tidal tails and the merging spirals I've shown over there simply because Andromeda and the Milky Way are spirals. And so at some point, 3, 4, 5 billion years from now, there may be this kind of gravitational exchange of material starting to take place with our two galaxies. And finally, I just love this particular example, so I wanted to show the space triangle. And what that is, you can probably figure out by thinking about it for a minute, is a galaxy on the left that used to be on the right, and the one on the right used to be on the left, and they passed through each other, and now we're watching them as they're perhaps again moving towards each other as they get ever together into the final state. But as they pass through again, lots of clumping of material and lots of starburst regions. So those are galaxy collisions / mergers. So now let's take a look. I can make this work. Okay. Are we online?
Yep.
Okay.
Yeah, you should be able to hit that. Watch on YouTube.
Okay. Let's see.
What? No. There you go.
Let me try it again here.
Nope.
Okay, where are we?
Yeah, let me take a look now.
There we go. Okay. There we go. Okay.
Hang on. Why is it not? Come on.
There we go. That's the end of it. Here we go. All right. I believe that's us spiraling around. And you see the counter in the lower right there. A couple billion years from now, and in our gravitational embrace is the Andromeda galaxy there. And you see triangulum, but it is not gravitationally bound to us. And here we are at 3 billion years.
AKA eminent.
Yeah. And finally, at about 4, there's passage, and this is what we believe is typical. You've seen some images that look sort of like that. And then slowly again through each other until finally everything, including the large black holes in the center, ends up merging. And the typical outcome is an elliptical galaxy. Now, I personally am going to be really excited to see what the Webb teaches us about galaxy evolution, because that's been sort of the intuitive understanding is we have these things with structure, and over time they do this and they end up like an elliptical, which doesn't have any structure. And that just made sense. But I think we are starting to learn already Can you go past this now?
Did you mean for the next video to play?
Yeah, no, there's no more
Okay.
videos, no.
Gotcha. You want to get back to the
Next.
PowerPoint?
Yeah.
You got it. I think we're
Okay.
back on track now.
Yeah, I think we're back.
You
on
try your
track.
clicker.
Thank you. There we go.
Good.
Yeah. Okay, so summary about galaxy collisions, they're very frequent. Is that me?
What is going on?
I think kind of nice. Okay.
Try your clicker one more time. Okay.
Okay.
Sorry
And
about that.
so we have the very unequal mass mergers that I talked about, like satellite galaxies, which don't modify the parent galaxy much at all. And we have the similar mass and very massive galaxy collisions and mergers that do in fact bring about great modifications to both galaxies. So that's kind of the summary of that. And one of these days, these two will come together. So now let's talk about star collisions in stellar neighborhoods. And we have never actually viewed a collision of two stars. Now, if anybody knows that not to be the case, please tell me. But I've looked and looked, and I believe it to be so, and it's not really surprising. But at any rate, we think we understand stellar collisions, and yet we understand that they happen rarely, and they don't happen in neighborhoods like where we are. And of course, our nearest neighbor is what, 25 trillion miles away, 4 light years away, Proxima Centauri. And that's not unusual for stars out here in these spiral arms. And in the case of our environment, we've now observed and counted on the order of 10,000 stars within 100 light years of the center of the solar system. Now that sounds like a lot, but 100 light years, 100 times 6 trillion miles, if you work out the volume of that, that's a pretty big volume for 10,000 objects. And that is, in fact, a sparse stellar environment. And now let's look at a dense stellar environment. And to do that, here is the, it is the Milky Way. It's kind of a general model also of spiral galaxies, where you have the bulge in the center, and you have the halo around it, and you have the disk, of course, moving out in a disk shape. And you see it says the sun there on the right. So this is in fact supposed to be the Milky Way. We're about halfway out, a little more than half, we believe, on one of the spiral arms. But what I want you to notice is those violet smudges, the globular clusters. And I imagine a lot of you, having observed globular clusters and open clusters and understanding that they have no relation to each other, what the globular clusters are is a pretty special thing. They're sort of miniature galaxies, or they're wannabe galaxies is the way I think of it. At the time that the galaxy was born, billions and billions of years ago, there were many clumps of stars, and they were all vying to be the one that collected up all the others and ended up being the galaxy finally. And it's sort of like the ones that didn't make it, but still had lots of stars that were all born about the same time, ended up being globular clusters away from the disk of the galaxy, away from the center, and orbiting the center. And so a typical globular cluster, one of my favorites, so is, you know, the great cluster in Hercules, partly because it's so dense that it just helps you to understand just what a difference there is to that and an open cluster, for example. But in the case of a globular cluster, and this one in particular, here there's about 500,000 stars within only a little bit larger volume than what we showed before that had 10,000 stars. So there's the difference between a sparse and a dense stellar neighborhood. And globular clusters in general have, you know, this many stars. And like I say, they were born at about the same time that the original galaxy was, which in most cases is very long ago. And because we understand stellar evolution, we understand that the largest, hottest, brightest ones burned out a long time ago. And so what you expect to find then in globular clusters is old stars that are smaller and dimmer and so on. And that is typically what we've seen, but there are some exceptions to that that we think we understand because of stellar collisions, which we'll talk about in a second. So back to our galaxy here. Now we've seen the dense environment on the outskirts there, above the halo in the clusters. Now let's look at the black hole region in the center. And at this point, while there are some exceptions, we have mostly found that there are supermassive black holes at the center of every large galaxy like ours. And so with that gravitational attractor in the center, and with the ability that Keck has given us here to look at the center of our galaxy, they've been able to spend over 2 decades there plotting some of the stars that are orbiting the black hole in the center of our galaxy, so that as they pass on their elliptical orbits, where they get very, very high velocity and on the close approach to the black hole, they have many observations, little balls that you see there on the orbits. And so that's given us the ability to understand this very dense area of stars around the center, around the event horizon of the black hole, and the stars zooming around it. And so let's just talk about the speeds at which they zoom by comparing it to what the Earth does. I don't know how many of you remember this, but I think it was the first general science class I took. They told us that the Earth was going 18 miles per second. And, you know, I was 9 years old or something. I shrugged and didn't drive a car, so I wondered how fast that was compared to our car. And eventually I understood that that was very fast. And yet I didn't understand why we didn't fly off it. We were going 18 miles a second, and I understood relativity later. So that's our speed here. It's very fast, but the speed of those stars as they go near to the black hole is in excess of a couple million miles per hour, and in some cases 5 to 10 million miles per hour. And so what you have then is a combination of dense star regions and high speed, which are the elements for this kind of a collision, a high speed collision, which what we've found is that it knocks most of the material off of the stars, and it doesn't create anything bigger. It creates 2 stars that have been stripped. And here's a nice, we've never seen one. Here's a nice simulation they've done of a 3 stellar mass and a 2 stellar mass moving towards each other and eventually passing close to each other. And then the result is, of course, the lower one is now on top, having lost a lot of its material, and vice versa, for a grand total of 71% of the material was stripped off of the stars. They're much smaller after the stellar collision, which makes, you know, that's pretty easy to accept and picture. You haven't viewed that happen yet. Now, the regions that are further out are much slower speeds for those stars, still in a dense neighborhood, that are going around the central black hole. And the same is true of the stars that are orbiting each other in a cluster like the Hercules cluster. And so when you have stars that aren't going at high speeds that approach each other, we believe that they merge. And so you literally end up with the sum of the stars. And then you have the mergers sequentially take place, and they get larger and brighter, till finally we have blue, big, bright stars in globular clusters. And so where we would expect for an old globular cluster to have nothing but old stars, we now are finding that there are large and sometimes large blue stars there, and we've given them a name, and it's blue stragglers. And I know that this is correct because I asked my AI, to tell me about blue stragglers. And 4 seconds later, gave me a nice explanation of it with citations and bullet points, and I don't know. I think we all have a future, but we need to work at that. At any rate, here's the real thing, where we see a globular cluster with quite a number of blue stragglers in it, even though you would have expected to find only old stars in these clusters. So the summary of stellar collisions, then, there are two environments where they take place: globular clusters and towards the black holes at the heart of galaxies. And the high-speed ones strip off the material, and the low-speed ones end up with these merged stars that can become quite large and blue. All right, now we're going to move all the way into our solar system, and we'll talk first about the beginnings of the solar system and some collisions from way back then, 4.5, 4.6 billion years ago. And here's a wonderful familiar view. There are many ways to look at it. This one has the planets all to correct scale, and the distances, of course, you could never get the correct scale on a meaningful chart. And so there we see the inner four, and then the asteroid belt, which again, when I went to school, was the only asteroid belt. And then finally, outside of the four giant planets is the other asteroid belt, the Kuiper belt. And one interesting thing we learned in the talks that we got about the collisions was that at the beginning of the solar system, during the formation, they have estimated that there was roughly 1,000 times as much material in those belts as there is today. And through the process of, I guess, some accretion, but a lot simply of the moving of the planets migrating in and out, a lot of the material was thrown out of the solar system. And so we have only a small fraction of what was once there, which makes me think, if we had 1,000 times more objects in the asteroid belt today that were colliding and deorbiting down to become near-Earth objects, I'm not sure we'd have a good day very often with all the near-Earth objects that there would be. But at any rate, they were cleaned up early. So now for some of the planet collisions that we have theories for. We have observed that Mercury there, of the four terrestrial planets, relative to the size of the core, has a much smaller mantle. And we believe it's because this very large projectile, roughly a sixth the size of Mercury, ran into it headlong early on and literally ejected about 80% of the mantle off Mercury. In the case of Mars, where we've been fortunate with orbiting spacecraft to have all kinds of full maps of the surface of Mars, this particular one is elevations, where blue is the deepest and red is the highest. And so one of the interesting things at a glance you see is that the northern hemisphere is much lower elevation generally than the southern hemisphere. And a lot of that may have had to do with this one simple collision, the largest one that we believe, that we know we've found so far in the solar system, of an impactor hitting the Utopia basin there and creating this massive depression. And so that's the result of a giant collision there. Here's a more familiar one that you've probably heard about, the giant collider theory for Earth, where a Mars-sized object, we believe in the first 100 or 200 million years, as the objects were actually being formed, they weren't yet formed and cool, slammed into the Earth and ended up pulling lots of the material out of the Earth and vice versa, and mixing together before the two objects finally ended up forming the Earth and the Moon, where that exchange of material did two things. It led to the fact that we have discovered by going to the Moon and sampling the mantle, that the composition of the Moon's mantle is very similar to ours. And we've also found that the Moon lacks an iron core, which it may have lost in that collisional event. So now we have this interesting feature of all 8 of the current planets where the spin axis is kind of what you expect it to be. The cloud of gas that formed down into the sun, which was spinning by the time it was formed, and then the disk, the protoplanetary disk, was spinning the same way, which we like to say from God's eye looking down is counterclockwise, but I guess you could look up from the bottom and say the opposite. At any rate, spinning the same way as the sun, and generally speaking, the accreted planets are spinning the same way with a couple exceptions. One being Venus there, which is very strange. If you've ever looked at the period, the daily period of Venus versus its rotational period, just look them up sometime and then think about what life at any point on Venus is like. It's strange. But the really odd one is the fact that Uranus got knocked on its side somehow. So its polar axis is pointing back toward the sun, which makes for interesting seasons as it goes around. And we believe that happened either pretty obvious from one large collision or several small ones early on. So those were all very long ago. And so what's happening today in the way of collisions? Well, we've talked about this in a previous talk, but here's a near Earth object that essentially did away with the dinosaurs and a whole bunch of other species about 66 million years ago, just north of the Yucatan Peninsula, Chicxulub. And it did a couple things. It did something else other than that. And one was that it sort of cleared out those dangerous animals and allowed for the fact that we could have a new niche for our particular species to evolve in. And therefore, humans occupy a niche that if it weren't for the fact that the dinosaurs, who lived much, much longer on Earth than humans have, if they hadn't gone away, it's not clear that we would be here yet. At any rate, that's an interesting fact. 66 million years ago. And then we have this one that is going to be the one that I wanted to turn the sound off for. But in this case, you see, looking through the dash cam there on the day after Valentine's Day, 13 years ago now. And this is in Russia, as you can see from the road sign there. Here comes this bolide, this exploding asteroid, which fortunately exploded at altitude and quite a distance away from the city, which is known as Chelyabinsk, and is quite a large city in central Russia. And the fact that it did that so many miles away, of course, meant that a lot of people observed the flash, and there was nothing to hear. At a mile every 5 seconds, sound took a very long time to come that 30 miles or so from the explosion. And when it did, a lot of them had called their friends and family and all gone to the windows so that they could watch when the... And so you hear the main problem, which was breaking glass. And not only did glass break, and this was an automatic camera sitting underneath the apartment eaves that just got knocked off its moorings there by the concussion. So lots of buildings were broken. Huge numbers of glass panes were broken. And there were, as you see, many people injured from the flying glass. And thank goodness it wasn't closer, because there would have been many fatalities. So an asteroid only that size, 20 meters, can cause that kind of damage. And so it becomes then one of our conclusions about what the risk is today. But let's just go quickly back through the solar system. So many planets early on experienced these giant collisions with a variety of results. A whole bunch of the material in the asteroid belts was removed early on. The massive impact 66 million years ago made way for the evolution of humans, we believe. And the recent impacts, which come, we like to say that size asteroid will hit us about once every century. And the reason we say that with confidence is it happened in 1907, and then it happened in 2013. It's about 100 years, so that's a good estimate for the frequency. We'll see if another one comes, 10 years from now or 200. At any rate, fortunately, none of them have been over population centers. Both of them have been incidentally in Russia. The first one was in eastern Siberia, and there were almost no people there. Okay, and then I've added to the talk that I've given to other people one final collision, which you folks might have guessed by now. It's the one that's the largest of all that we didn't actually have evidence of until about, what am I going to say? Let's see. You'll see in a minute. 11 years ago, when LIGO made its observation of a gravitational wave.
After this commercial break. Where's the skip?
It's 15, so here it comes. There we go. Okay. There we go. So we have two black holes approaching each other. You'll hear the statistics on it in a minute so you can understand what you're seeing here. And you won't be surprised when I say to you that this is a simulation. So there we have the event horizons coming together with their material and creating one final one. So a whole bunch of people involved in this. Can I go back to the slides now?
Yep.
There we go. Okay.
Picture's good.
Yep, thank you. So what we see there is not actually an image. It's what we have now simulated on a computer that was GW 150914. And so it's easy to break the code. GW is the designation you'll see for gravity waves. 15 is the year, 914. Okay, so you now understand how to understand the actual timing of an observation. This was the first one ever directly detected, and I'm sure you heard about it. And it's a computer simulation of this particular binary system of planetary black holes. And we'll talk about that in just a second. But one of the things you noticed is that the star fields are really, really distorted during these events because you actually have a distortion of space-time. So like the first things I said about pondering where space exists, if there's no space for it to exist in, I want you to just try to think about what space-time being distorted means. And what we know it means at least is that it creates a gravitational wave that as it moves through space with a particular frequency can now be sensed by these long baseline, very, very sensitive instruments that are gravitational wave sensors. And we don't yet have one built that has got a long enough baseline. They're planning one to be launched into space to observe a black hole merger that is from two massive black holes in galaxies merging. This is a merger of two what are called stellar mass black holes. And you're probably aware that that's one of the ways black holes are produced. They come down, they end up probably going through a supernova or a hypernova phase. And then what's left at the end is a black hole. But what the progenitor is something that's a much, much larger sun than our own. Maybe 20, 30, 40, 50 masses of the sun, very large ones. In this case, we have calculated that it was a 36 solar mass black hole and a 29 solar mass black hole. And you add those together, this is fun to do, it's simple, and you get 65, which isn't what the big one that's left is, 62. And so what happened to the three solar masses? And that's just kind of an amazing thing. Good old Einstein. So three solar masses, when you work this out, the peak energy in the last third of a second there as they finally came together was that many watts. Now, I don't know what that means, except that anything that's times 10 to the 49 is pretty big. And so it's a level like the combined power of all the light in the observable universe at the end of that merger. So there's a powerful collision.
Hmm.
And it's radiated as a gravity wave. All right, thank you.
Wow. Questions for John?
It seems like that gravity wave was produced a big hiccup
Yeah,
for a long way.
yeah,
So is it, but for us, when we saw that one, it was barely detectable, right? Of course, that was a solar mass black holes.
well, this was a solar mass black hole.
Okay.
This was two, let's see, the term is not solar mass, it's stellar mass.
Solar mass. So
Yeah, a sun won't produce a black hole, it's too small. But the ones that are much, much larger progenitor stars are the ones that are candidates to become black holes. Just like the ones that merge together, like the one we saw, and through a period of time become perhaps the supermassive black holes at the center of galaxies. We're just starting to understand this.
okay.
But the wave, yeah, I don't know. And I don't know if there's anybody that can actually give you a physical feeling for what that wave is. I do know that the ones that are smaller, like this one that we just observed, because they're stellar mass, as opposed to a supermassive black hole collision of two that must happen when two galaxies come together and end up with a central supermassive black hole. In that case, those are very low frequency, very, very long wavelength, which is why we need to get our baseline up in space to have enough distance between our sensors to be able to measure. You know, I didn't actually put up the statistics, but it's an extraordinarily sensitive gravitational sensor that can sense, I think, on the scale of something like, if the baseline were from us to Proxima Centauri, 25 trillion miles, the movement is about the width of a human hair. Wow. Okay, but we've got detectors now that Einstein, one of the things he said when he had given his theory and then talked about it later in the 30s and 40s, was that he didn't believe that humans would ever be able to come up with a technology to sense a gravitational wave. So the people that did it are pretty proud.
Yeah. Now who's the dummy?
Yeah, right. Yeah, made it real.
Way to go, Einstein.
Yes,
John, you talked before about the globular clusters that are
yeah,
that
beyond
are
the halo.
rotating,
Yeah.
revolving
Orbiting,
around the center of the
orbiting,
black
yeah.
hole. They must at some point go through the plane of the galaxy, right?
Mhm.
Plane of the Milky Way.
You know, that's a very, very good question. Yeah, I think the answer must be yes. Yeah.
And
I don't think they're so far out that they're beyond the distance of the arms, but I'm gonna look into that. That's a good question. Yeah, I mean, the arms are roughly 100,000 light years across for the Milky Way. And it could be that most of them are beyond 100,000 light years.
Is there a space-based gravitational wave detector in the works?
There's a pair. One's in Louisiana, one's in Hanford, Washington. That's LIGO.
Yeah, easily.
Oh.
Is that space-based?
Oh, it's space-based. Yes, there is at least the concept, and I believe it's the Europeans that have it.
Okay.
It
It was obviously easy to come up with the
answer,
concept,
the answer
but
is, yeah, the answer is yes, but they're working on planning it out.
wow.
How big did you say the asteroid that hit Chelyabinsk recently? That's the recent one, right?
Yeah. Yeah, 20 meters.
20 meters. Look at, is it, space weather, and they show the chart showing the size of the different near Earth objects and how close they are.
Hmm.
The one that hit Russia, did we know that was coming? Was that detected?
No, it's a very interesting story about that day, the 15th of February. Let's see, the guy that was named one of Time's top 50 young men in about 2010 happened also to be running the JPL Caltech planetary, well, at the time it was just called the asteroid program, okay, the near Earth object program. He gave us a talk about this, and he said that his group had predicted one that did in fact pass very near to the Earth, inside the orbit of the geosynchronous satellites on the afternoon of the 15th, okay? So he had to go to Washington because that was a big day for him to talk about that. And that was 9 o'clock Russia time. So at like, what, 2 in the morning or something, this happened in central Russia. And all the people in Washington that were waiting for the NASA guy to come to talk about the asteroid that's coming wondered if it had come early. And so he had to explain not only what was about to happen when he got there and talked that day, but why they didn't know about the one that was coming at 2 that morning, because they didn't. It came from the direction of the sun. And if the current administration doesn't stop it from happening, we're finally going to have a satellite between us and the sun that's going to allow us to see a much larger swath of the sky in towards the sun. Because all these surveyors that we have now, surveillance telescopes on the ground and in space, can't really look very close to the sun for near Earth objects. And so we know that there's a hole in our understanding. And, you know, eventually everything will pass out here somewhere. But the fact is that this one apparently had been coming for some time from a direction that we hadn't been looking in, and they got us. Yeah. Anyway, but that was quite a story for, the guy's name was Chilkos. He left NASA shortly after that, but not because of that.
Other questions? Anyone online?
You're snoring.
Well, if not,
Thank you.
John, thanks again. And as always, keep your eyes on the groups.io until the next meeting, and please join us for refreshments in the library. Thanks to Diana.